In the last video, we talked about Fourier cosine and sine series. And the idea was that if you have a function f of x defined on the interval from 0 to t, then it will have an even and odd 2t periodic extension. And then the Fourier series of those are going to be the Fourier sine and cosine series of the function f of x. So the Fourier cosine series is the Fourier series of the even periodic extension and the Fourier series of the odd periodic extension is called the Fourier sine series of the function f. And in this video, we're just going to look at a simple example. So let's say that f of x is equal to 1 if x is between 0 and pi. So between 0 and pi, the function is just 1. That's your function f. Well, what are the Fourier sine and cosine series of it? Well, this function is going to have an odd periodic extension. So odd pi periodic extension, that's a little too far. Like this, right? It's just going to go from negative pi to 0. It's going to be negative 1 when x is between negative pi and 0. And then it's just going to keep repeating itself forever. So that's the odd periodic extension. The Fourier series of this is the Fourier sine series. So let's calculate the Fourier sine series of this function f. Well, that's going to involve the bn's, which is 2 over t, well, t in this case is pi, and the integral from 0 to pi of f of x times sine n pi x over L, or n pi x over t, and t in this case is pi, so you just get sine nx. So this is going to be 2 over pi times the integral from 0 to pi. My f of x is just 1 from 0 to pi, so the integral from 0 to pi of sine nx dx. And this is going to be, so we integrate by substitution, we get 2 over n pi times negative cosine nx from 0 to pi. And now we evaluate the integral, so negative 2 over n pi times, and I have parentheses, cosine of n pi minus cosine of n times 0. It's cosine of 0. This is going to give me negative 2 over n pi times cosine of n pi is negative 1 to the n, and then cosine of 0 is 1. And if you want to make this a little simpler, you can distribute this negative sign inside the expression, so you get 2 over n pi times negative 1 to the n plus 1 plus 1. And this is actually going to be, if n is odd, then n plus 1 is even. So negative 1 to the n plus 1 is just going to be 1, and then you have 1 plus 1 is 2. So you get 4 over n pi if n is odd, and if n is even, then n plus 1 is odd. Negative 1 to the n plus 1 is negative 1. You add 1, you get 0. So you just get 0. So the Fourier sine series of the function in this example is, well, I can write it as the sum from n equals 1 to infinity of 2 over n pi times negative 1 to the n plus 1 times sine of n x. And to write what this is, and to write some terms out, it helps to use this format because I can see that I only care about what happens when n is odd. And I'm going to have this 4 over n pi is 4 over pi times 1 over n. So I can factor out the 4 over pi and then just plug in what I get when I have n is odd, right? So this is going to be the sum for odd integers of 4 over pi times sine nx over n. So that's going to be sine x plus sine 3x over 3 plus sine 5x over 5 plus sine, oops, the sine is on top. That's my mistake. Sine 5x all over 5 plus sine 7x all over 7 plus dot dot dot. And if you graph this, you'll see that the graph is squiggly, but it does, as you increase the number of terms, it will look something like this. It looks like this. And it just goes on forever like this. And as you add more and more terms, the squiggles get less and less. There are more squiggles and they're less and less high. So they're smaller, but there's just more of them. And as you go out more, it'll look more and more like a straight line. And by the way, what happens when x is 0 in the Fourier sine series? You should get 0, right? You should get y equals 0. So the limit, if you imagine going out forever, add all the terms, it's going to pass through 0, 0. Because there's a theorem that says that the Fourier series will converge to the halfway point of the two left-hand and right-hand limits. Right, so the right-hand limit is 1, the left-hand limit is -1 as x approaches 0, and then the average of -1 and 1 is 0. And then you can actually see what happens if you plug in 0 in for x, right? Because you get sine of 0 in all the terms, and that's 0. Another way you can see why you would get 0 is because this function is an odd function. The Fourier series, the Fourier sine series is odd because it's just a bunch of sine terms. So when you have an odd function, when you plug in 0, you have to get 0. And I'll let you think about why that's true. I mean, if you think about the 180-degree symmetry, right, it kind of makes sense. So that's the Fourier sine series. Now let's do the Fourier cosine series. Well, the Fourier cosine series, let's think about what it should be. The Fourier cosine series is the Fourier series of the even periodic extension. And from 0 to pi, so you have this function that's 1 from 0 to pi. Okay, to make it even, you reflect across the y-axis. So that's going to be like this. And you can fill it in at x equals 0. And then you just repeat, right? You take this and then you shift it to the right and left forever. So it's actually just going to be a straight line. It's just going to be y equals 1. So I shouldn't use f, maybe. I should use, I don't know, g for the even 2 pi periodic extension. It's just going to be 1. Okay. So what is the Fourier cosine series going to be? Well, it would be a sum of cosines, but there's the a sub 0 term. Right? So take a moment and think about what it would be. Okay, I'm going to check and make sure that the Fourier cosine series, yeah, it does involve the A0 term. So this A0 over 2 is the constant term, right? So this function is a constant. So the Fourier cosine series should just be 1. That's what the Fourier cosine series should be. So let's check that this is in fact true. Okay, so the Fourier cosine series should be just 1. I mean, we didn't check it. We're going to check that it is in fact 1, but intuitively it should just be 1 because you have this A0 over 2 term, right? So your A0 should be 2 and then everything else should be 0. And let's check that. So my A sub n is 2 over pi times the integral from 0 to pi of f of x times cosine n pi x over pi, so that's going to be cosine n x. And when, okay, so my f of x from 0 to pi is just 1, so I just have 1. So I'm integrating cosine nx, which I'm pretty sure we've done in a previous video, but the way you do it is you calculate a sub 0 first. It's going to be 2 over pi times the integral from 0 to pi. Cosine of 0x is 1 dx, and so this is just going to be 2 pi times pi, or 2 over pi times pi, that's 2. Okay, and when n is greater than or equal to 1, then we can do a substitution. So I'm just going to write this out again. Integral of 2 over pi times the integral from 0 to pi of cosine nx dx. And then this is going to be 2 over n pi times sine of nx from 0 to pi. And what is this going to equal? 0, right? Because you get sine of pi n minus sine of 0. And when you have n as an integer, sine of pi n is equal to 0. So you just get 0. So what that means is that the Fourier sine series, cosine series of my function is, remember the general formula, it's a0 over 2 plus the sum of an cosine n pi x over pi, because my t is pi, so I just get a sub n times cosine of nx from 1 to infinity, but my an's from 1 to infinity are all 0, and my a sub 0 is 2, so what I'm left with is 1. So that's the Fourier cosine series of my function. Okay, that's just a simple example of calculating the Fourier cosine and sine series.